Welcome to this presentation on transient energy analysis. If you want to follow along with a handout, you can find that link to that in the description. And let's get into it. All right, so you can see where we're at here in the midst of the forest. We're going to go to the transient energy analysis. Actually, the thermodynamic relations is going to be later on, but then we'll get an ideal gas mixture next, and then psychrometric applications. All right, so what we've done so far, a lot of the analysis that we've done has been steady state analysis, mainly that the right-hand side of this equation is 0. So what does that mean? It means the mass of the control volume, because we've been using a lot of control volume or control system analysis, doesn't change with time, so it's 0. All right, there could be some inflow rate, there could be some exit, but the change of what's in the control volume doesn't change with time, both on a mass basis and on an energy basis. So we can see here the enthalpy, velocity, so we have a kinetic term, we have a potential energy term, the work, net work, the control volume, and the heat transfer. Again, all that doesn't change the energy of the control volume, what's in the control volume. It's a steady state occurrence. So we're going to change that now. So some places where this exists is in a turbine, especially when it's starting up, as well as pumps. As they're starting up, things are changing. They're getting up to speed. So you're going to go from maybe cooler conditions initially to hotter conditions, or low pressure to higher pressure. Other places are with compressors. So we start at a low pressure, work up to a higher pressure, or a tank's filling or emptying. And so the amount that's being stored is increasing and decreasing. So the way we do that is we start off with our, at least on a mass basis, start off with our mass term now here on the right-hand side. It's a function of time. So we're going to take the differential with respect to time of the mass within the control volume, and it's going to be equal to the rate of what's coming in minus the rate of what's going out. All right, so if we integrate all those over time from 0 to t, we see the left-hand side goes from what's the mass in the control volume initially at time 0 to the mass that's in the control volume after some time t. Okay, that's pretty easy. On the left side, we still got these integration terms, and it cleans up pretty nicely in that we just have the sum of all the mass that's coming in minus the mass that's going out. So as long as it's a nice clean value, we don't have to worry about, so this is mdoc, so it could be rho, density times area times velocity. As long as all those things are relatively uniform, we can go ahead and use these clean mass values, mass at the inlet minus mass at the exit. All right, so this is the main equation we're going to be working with on a mass basis. On an energy basis, we have our same standard equation on the right-hand side, but instead of 0 on the left-hand side, we'll say, hey, what's the internal energy of the control volume? How does that change with time? Right? So if we integrate with time, we get these terms here. So what's the internal energy initially at time 0, and what's the internal energy after some time t? You can see now instead of a rate for our Q dot or heat transfer rate, it's now just the total heat transfer minus the total amount of work done. And then we have the integration terms of mass m dot times our enthalpy. Sorry about that. So we have to make sure we integrate those appropriately and include those in our calculation. So we'll get to do that in the example. So here's example 1 that we'll be looking at. We'll do this in class. So yep, just be ready, and there's probably great equations that we just talked about, the boxed ones, to add to your equation sheet. All right, so I'll see you in class, and I hope that was helpful.